To start the evening with a bang, we have Rokhaya Falls, master student at the PFL, and Luca Di Bartolomico, PhD student at the PFL in system security. Then we talk about binary similarities and what happens when mixed with machine learning. Please give them a warm welcome applause.
Hi everyone, can you hear me? Okay, nice. Thank you for coming. So I'm Luca, this is Rokhaya. We're researchers at EPFL. We are long-time CTF addicts. If you played Lake CTF or anything, you might know us. We're the people behind it. Anyway, hello. We want to talk about binary similarity today, which is the problem of who's that Pokemon, but with elves, right? With binaries. Now, it's a very hard problem, and at the same time, no one cares about it, which is a perfect topic for a CCC talk, right? So that's why we're here today. Now, our idea of this project was we wanted to do this on Android, right? We wanted to download a bunch of apps. We want to build some binary similarity framework kind of thing and detect when vendors apply custom patches to libraries because vendors are bad and they're going to be vulnerable, right? We also wanted to check for outdated libraries, right? And in the end, maybe make a paper about it. I don't know, citations, I don't know, something. Now, before we get into the meat and grind of this paper, there is a preface I need to do. There are some facts you need to understand that will help you understand why did we make some choices in this talk. So, fact number one, you need to understand that my therapist told me I need to stop blaming everything that happens to my ADHD, which is very linked to fact number two, I don't trust psychologists. I think they're a weird class of people. You need to be a special kind of crazy to talk to crazy people all day, right? And the third thing is that this is why this whole project got sidetracked, and I blame it on my ADHD, because in fact, we never got beyond step one. That's the issue, right? We got stuck there, we got stuck in a million rabbit holes, and you will see why later. So we're not the first people to try to do this on Android. There was a project before in 2021. This paper looked at the top 200 most popular libraries, apps, sorry. They extracted some features you see on the column on the left. They extracted the globals, the imported functions, the dependencies. They also had some heuristics based on version strings that could appear in those binaries to find which ones are outdated and not up to date, right? And they found that actually it was pretty bad. However, the study was limited to the top 200 most popular libraries, right? We wanted to expand this and have a much larger sample of apps, right? Now, when we're going to discuss the techniques we used, unfortunately, we're going to touch on some sensitive topics that might trigger some of you in the audience. Unfortunately, we need to talk about JavaScript. We need to talk about academia. And worst case, we really try to avoid it, but yeah, we're going to talk about machine learning, right? Now, we begin by describing the dataset. So we wanted a large sample, right? So we used Androzoo, which is this project by the University of Luxembourg that lets you download APKs. We wanted to download all the apps that had at least 10,000 downloads on the Play Store. Now, unfortunately, when I wrote this script, while debugging it, of course, I get commented out the line filtering this, and when I ran it, I kept it running on a server, of course, and then turns out I downloaded everything. I downloaded every single app ever published for any app store on Android ever, including App China, F-Droid, and so on, which is a massive data set, right? But it was too late to go back, right? So we said, okay, let's just do very, very large statistics. If there is anyone from the University of Luxembourg, I'm sorry, I didn't want to download the 11 terabytes of data from you. We did use the zip file trick, because APKs are just zip files. We didn't want to download the whole app, we just needed native libraries. And as you know, zip files have an end of directory record. And if the web server supports the HTTP range header, you can just download specific files. This saves you an order of magnitude of bandwidth. There are Python packages that do this for you. You don't need to implement it. Another issue we run into is, well, Btrfs, because, of course, our disk was not large enough to store all of this. So we decided to be lazy and use this tool called btrfs convert to live convert our file system for btrfs because it has compression, right? Now, on the Arch Wiki, if you go on the page for btrfs, there is this red banner, right? It's very visible, right? And we did read it, and we decided to ignore it. I have to say, yes, our file system did get corrupted. Luckily, we didn't lose too many files, but this is where we have our first takeaway. In this talk, we're going to give you a list of takeaways, of lessons we learned, right? First lesson is, you're not smarter than whoever wrote the Arch Wiki, right? Yeah, just follow it. But once we downloaded the dataset, we already had some interesting statistics, right? So in about 8.5 million apps, we have 12% which have native libraries. And there are around 1 million unique binaries we were able to extract from those APKs. An interesting fact is that the vast majority of those libraries are reused among apps. In fact, if you look at the last line, the top 5,000 binaries account for 77% of all library usages across all datasets, right? So libraries are almost never customized, we found out. Everyone uses the same, right? Which is going to be important for later. Now we need to go and start talking about what we did for the binary similarity. And we tried 4 different approaches, right? Quite a lot. We are going to organize them in an alignment chart because some of them are more lawful, some of them are not so much. You will see why. We start with the lawful ones, which is going to be machine learning, because this is what academia told us to do. You should use machine learning to do binary similarity. In the past 5 years, this is the main method that was used. And now I leave the floor to Rokaya, which will explain to you what we did.
Okay, so as Lucas said, we need to talk about machine learning because most of the recent papers that come out on binary similarity use machine learning models. So first things first, you won't believe it, but we are not machine learning experts. You'll quickly realize it because what we use with machine learning didn't work, and we quickly realized that the tools we were using were not really plug and play. We had to actually do quite a bit of patching to get them to work on our data set and to get them to run. There are millions of different binary similarity papers and models. We chose only 2. One that's a little bit older, a little bit simpler, and one that's more recent, state-of-the-art, uses NVIDIA GPUs, very fancy stuff, right? So let's talk about the old school ML. Do you remember when machine learning was called machine learning and not just AI? Do you remember when you found it exciting and you didn't cringe as soon as you heard the words machine learning? And do you remember Word2Vec? If you've never heard of Word2Vec, here's a quick refresher. Basically, it tried to reduce linguistic context out of words by putting them into a vector space. And most of the binary similarity papers actually do the same. But instead of mapping words, they do it, it's even better, it uses assembly code. It maps functions into vectors in a dimensional space and creates embeddings. Then using cosine similarity, we can determine that vectors that are close points will be similar functions. For example, if we take a function called loginfo and a function called logerror, these functions should be quite similar. They will map to vectors that are that will have a high cosine similarity. But if you were to compare them to a hashing function, the cosine similarity would be quite low because the functions are not similar. So the first model we played around with was asymptovec, and it builds upon that. It's quite old. It's from 2019. That's very old in ML world. It converts assembly functions to feature vectors. The thing is, we can't directly apply Word2Vec because natural language, you can go from left to right and understand the whole sentence. But when you're working with assembly code, you need to understand the overall structure. You need to take into account the control flow. So asymptovec uses random walks to generate path along the control flow graph and enhance it so the model better understands the structure of the program. It uses CPU only, believe it or not. A machine learning model only uses CPU. So it has quite low hardware requirements and is super cheap because it uses only 3 cents an hour. We determined that this was lawful good because it's very cheap, very expensive. We don't need to go broke. The second approach we tried was to join the AI hype by using transformers. This was done with JTrans, which dates to 2022. It uses a transformer encoder architecture to customize to better understand assembly and better deduce contexts from assembly tokens. It's jump aware in the sense that it marks jump origins and jump targets with a similar token so that the model is more CFG aware. It's a little bit more expensive than ASM2VEC because it actually uses GPUs. It uses 8 NVIDIA A100 GPUs and 768 gigabytes of RAM in the original paper. This comes around to $2.73 per hour, which is 90 times the cost of ASM2VEC. To give you a better idea of how these models perform, this is a graph taken from the JTrans paper, where they conducted an experiment where they compiled the same source code with O2 and O3 levels. And what's relevant to us here is JTrans and ASM2VEC. You can see in blue, JTrans performs better than all other models, and it's followed closely by ASM2VEC in red. But there's something quite interesting with this graph. As the pool size grows, the performance decreases. And like Lucas said, we have quite a lot of data to run into, so quite a lot of functions. So we're wondering if we actually run it on our whole data set, would we get results at all? Well, here comes another issue, is we can't actually run it on our whole data set because JTrans is actually pretty expensive. On a total data set of 350 binaries, this comes around to 3.2 million functions, it took 12 hours to create embeddings. So if we were to run it over on our data set of 1 million libraries, it would amount to 38 years, 4 months, 8 days. We would like to leave our universities at some point, so this is not possible. So to recap, 2 problems. First one is, would we get a performance? And second one, would we actually get results if we have to run the models for long? So after heavy consideration, we decided that the problem is not that our data set is too big. The problem, and this is the third takeaway, please remember this. The problem is ML papers are like Disney movies, you know? Everyone loves them, but are they realistic? We don't know. Not for evil.
So now we talk about the chaotic methods. This is stuff we did while we were trying the ML stuff. This is where we got on a million rabbit holes I was talking about. And they provided some interesting results. Sometimes you get sidetracked into the right thing. And in our case, what piqued our curiosity was when we were drawing some statistics on our dataset. So here it's a plot of how much shared are libraries. You can see by hash how many apps are using that same binary. Now, if we zoom in, you see that there are libraries that are used by more than 10,000 apps. But the plot is weird. It's not smooth. There are stairs. You see, there are parts in which the plot is flat. This is very weird. We thought it was a problem, but actually, no, it's true. And this suggests that there is a library that maybe made a release as a tarball or something, and then developers just downloaded this tarball into their file system, and they just kept it as it is. And many, many people do this. It feels like there is this trend of getting libraries from somewhere and then never updating them, right? And it took us a long while to figure out where are those tarballs coming from. The answer was very obvious, actually, in the meantime. If you ever developed an Android app, maybe you know this already. But it's this. It's from Maven. Maven is the central Java package repository, but it's also used for Android, also for Android native libraries. In fact, when you build an Android app, you're going to use Gradle, right? Even if you use Android Studio, that's just a very, very bloated wrapper around Gradle. And if you're in your build.gradle, you add this line that you see, dependencies, implementation, pl.droids. This is the most popular GIF drawing library in Android. Gradle will fetch this URL you see on the bottom, that if you visit it with a browser, it looks like this. Right? It's a HTTP directory listing. The files Gradle are going to look at are 2. The .aar, which is another zip containing the libraries themselves, and the .pom, which is metadata, which will tell Gradle what are the dependencies, do I need to download other packages to support this, who's the developer of this, what is the version, what is the URL of the GitHub repository of this library. All information that were extremely, extremely nice, right? What was even nicer is that Maven itself supports HTTP directory listing, even on package names. So we could download every single native library ever published to Maven, calculate the hash, and see if it checks out in our database. We did that, and surprisingly, Most libraries come from Maven. Well, not most, but a bunch of them. 29% in our data were directly matched. And this was a great result for us, because now we can immediately identify 1/3 of the libraries without need of heuristics, without need of imprecision, without need of AI, right? Especially, it was very nice for us because it gave us ground truth through which we can evaluate the machine learning models we talked about before, right? However, instead of stopping here, this was just a gateway to many more rabbit holes. One of the main ones was React Native. React Native is the most popular native library in Android. In their Maven package, most of the versions are missing. You can see here, it stops at 0.20.1, and then there is nothing until 0.71. And it's not even the last version. That's 2 years old, right? And we wanted those versions because we knew a lot of packages were using React Native, right? To understand what was going on, I need to give you a small lecture on the tragedy of React Native on Android. Here's what happened, because it will let you understand why is the ecosystem so bad. Because this should be a very, very prestigious library, or at least well-maintained, right? So it starts on January 18, in 2016, when a developer uploads a markdown file on their GitHub saying he's unhappy with the Maven repository. Because it's tedious, requires human verification every time you upload a new artifact, and also it's slow to propagate builds. So they said, okay, what if we just, since we're JavaScript developers anyways, let's just use NPM, right? Stop doing Maven. 3 weeks later, this proposal was approved. Also, one of the reasons why he said, look, this is going to just add 3.7 megabytes, and your node modules folder is huge anyways, right? So why would you care, right? Remember this sentence. Now, you might notice that only 3 weeks passed between the proposal and the acceptance of changing the publishing distribution platform for your package. This is why, because JS developers move fast and break things, and in this case, they broke a lot of things, actually. People were still opening issues years later because their build system was broken, because they installed a React plugin that was expecting a different version. Why? Because no one updated their build Gradle. Everyone was still using the last Maven version, the 0.20.1, the last one that was updated, right? It got worse and worse with time. 1 year later, someone was able to impersonate Facebook and publish another React Native version to JCenter. The JCenter developer stepped in, there was a lot of drama. Also, allegedly, this version was not malicious. It was actually React Native by a developer, which was probably very disgruntled with this NPM thing. Anyway, the story ended 2 years later when Facebook just decided to lock all the issues about this and limit the conversation to collaborators. So we realized, okay, the missing versions are on NPM, fine. We're going to download stuff from NPM, and we got most of the versions, except the last 2 years. And we're still wondering what happened in the last 2 years, right? And it's because the story of React is not done yet. There has been a second war on their own users in 2022, when, unfortunately, another React developer claimed that the 3.7 megabyte figure from 6 years ago is not up to date anymore. It's now more like 126, right? And it's too big. Because NPM was not accepting the package anymore. Not because NPM has strict size requirements, but because the way you upload a package to the registry is super cursed. They do base 64 of a whole tarball, and then use the 64 as a put query to the registry web server, and the web server just rejects stuff that is too big, right? So this was not intended, but so after months of deliberation, the React developers decided that the best option was to go back to Maven under a different artifact name. That's why we're missing those versions, and breaking once again everyone's build system, right? But for us, it was good news because we were able to find this new artifact name and get the missing versions. And integrating them into our dataset yields a much increased detection rate of 60%, almost, which is crazy that 30% native libraries are React, but what can we do? The takeaway from this is that you should go and do rabbit holes, get sidetracked, go do your side quests. Don't adhere to the schedule. I don't know, sometimes it works, right, in this case. Now, also having so much ground truth gave us the opportunity to do some more in-depth statistics on how actually outdated native libraries are. I'm just going to give you one example because I think it's very representative. So do you remember the GIF library from before? It had a very important CVE in 2019. There is a double free every time you displayed a peculiar GIF. A lot of apps were impacted, even WhatsApp, because this library was very popular. So he said, OK, how many apps are still vulnerable to this? How many apps did not update libpl droids on roids? In our dataset, we had 45,000 apps that use this library, right? And this CVE is 6 years old, right? How many do you think? Well, it's not high enough because the answer is 78% still were vulnerable to a 6-year-old CVE. If we restrict the apps that are available today on the Play Store, the figure is slightly better to 58%, but basically everyone is still vulnerable, even including very, very popular apps. For example, apps with 140 million downloads, 240 million apps downloads, and the worst one by far was Update News for Samsung, which maybe you don't recognize, right? This is pre-installed on Samsung devices, right? Has 400 million downloads, but if I tell you the package name, I'm pretty sure you will notice some familiarity. te.axelspringer.diana.0 page, and yes, it's those people. It's those people that had a contract with Samsung, and they ship a vulnerable library. Now, this doesn't mean it's exploitable, right? Actually, for most of those apps, this is not exploitable. We looked into this app, and we saw the only GIF it displays are GIFs that are already included in the APK. It doesn't get it from remote. In my opinion, this is not an excuse, because the code might change anytime soon. A developer might change it to display remote GIFs, and then suddenly it's exploitable, right? So, takeaway number 5, no one updates native libraries. This thought never crossed the mind of an Android developer, right? We complain about package managers, such as pip, such as NPM, but Maven is much worse. As far as I know, Gradle doesn't give you auto-update functionality. It doesn't check for updates of a given native library. So there's that. This was the third approach, Digital Good. It was quite successful. However, there is one more, which is evil. You will very, very soon understand why. The idea from this came once we were trying yet another AI tool to detect version libraries. This is called MLM. It's only accessible to Chinese citizens. Luckily, we had some Chinese friends that very kindly gave us access to this. And it was unable to recognize a very simple FFmpeg library, right? Which is weird, because like, the library was very small. If you just write strings, you will see that, of course, like this is, those are the things. For who doesn't know, libbaby is the old name of FFmpeg, and it's everywhere in their code base. You really couldn't mistake this, even if someone is not experienced reverse engineering this. So we got curious and we saw, is it possible that those people are not looking at strings? Turns out it's true. Most binary similarity tools are not looking at data, right? They only look at code. Some of them even ignore constants in the disassembly, immediates, right? Which are super important to detect, I don't know, cryptographic primitives, for example, right? And this is where we got the idea. Okay, what if we actually look at those? What if we implemented the stupidest binary similarity algorithm on strings, right? What's going to be the performance on this, right? So we're going to show it to you live, the performance of strings. We have, let me see if I can show it to you now. Yes, so in this folder, I have this beans folder, in which I have a bunch of hashes. Those are all the versions of the GIF library I showed before. It's very small, 2 megabytes. And I also have this script that converts the hashes to the correct version. You can see we have 114, 1220, and so on and so on. I'm going to see if a stupid bash script can detect who is the closest match between those two binaries, right? Now, I have some additional restrictions for this bash script, because otherwise it was too easy. So first restriction we're going to do is that we're going to only use core utils. Second, we need to beat the state of the art. And third, the demo is not just going to be running the script. I'm also going to implement it in front of you. And I need to... Yes, I'm going to try to make it in less than 60 seconds. I don't promise anything during my diagrams. I was not always successful. Anyway, let me open a random script. Let me bring up a timer. Let's see if I can do that. So, okay, first thing we do is that we create a temporary directory. And in here, we're going to store the results of strings. We sort them, and we strip the base name. And we send it to the background to be a bit faster. Then we have a double for loop over this, over the generated strings. We pay attention not to compare the same binary against itself, classic mistake. Then we grab the number of common lines with the com tool, which is the opposite of diff, for who doesn't know. If this is higher than the maximum we ever saw, we update the maximum and the file we got it from, so we can just print it. And we just need to initialize those two libraries. And what did I miss?
$file is not defined.
Sorry?
No, never mind, never mind.
What did you say? I'm inside the wrong directory. Ah, you're right, you're right. Oh, yes. I was worried about the CC crowd because it's so much better, you know, you really cannot fuck anything up when you do a CC talk. So let me remove this file. And there we go. Okay, that was a bit over time. Let's pretend this didn't happen. Now, to check that this is correct, we can run this through the version conversion thing. For example, it tells me that 114 is close to 116, 128 is closest to 129, 119 is closest to... So it can work, right? But we want to give it a score and compare to the other tools. So we prepared 3 small benchmarks, right, to run this on. The one is this GIF library I showed you. That's 48 binaries. It's super small, only 2 megabytes. The second one is libsignal. All the versions we have of libsignal that we took from Maven. That's almost a gigabyte of code. And then we have libvlc, right, which is somewhat large, almost 6 gigabytes, right? To give a score, we use the simplest scoring thing ever. So if I ask you what is the closest to 124, the correct answers are either the next version or the previous version we have in our dataset. It's pretty stupid, but it's better than nothing. We have a number. So now let's compare the different approaches, right? Now, one gave us the ground truth, so it's excluded. On the small dataset, the GIF one, async-to-vec performs quite well, runs in less than a minute, and the score is 85% correct. JTrans also works quite well, 93%, and the bash version instead gives us 83%, so not always correct, 3rd place, right? However, we now move on to the slightly bigger benchmark, right? And by bigger, I mean this is still incredibly tiny. We have 1 million binaries in our dataset, but still. Here async-to-vec struggles. It takes almost 1 hour, and the accuracy is 11%. Now, the asterisk 22% is because while we were working on this a couple of months ago, the JTrans developers made another paper in which they said if you filter out small functions, functions with less than 5 basic blocks, the accuracy will increase a lot. So we did this, and actually it does. Accuracy doubles. Same for JTrans. Although it takes a bit longer, accuracy is still quite high at 80%. However, they get all blown out of the water by this simple strings approach, which is still pretty much instant. Moving on to libvlc, results do not look great. So async-to-vec goes out of memory. This was run on a 512 gigabytes of RAM machine. It was not enough. JTrans didn't finish. We had a timeout of 24 hours. We tried a couple of times to optimize it, but since it was expensive to run it, we just gave up. It was always using more than 24 hours. And to be fair, it didn't really matter because the bash version is still, you know, so of course the bash version is a joke, right? Of course it cannot be a substitute. What I would like to give you the takeaway of this is that we need better benchmarks. Maybe artificial intelligence works well only on artificial benchmarks. And yeah, that's pretty much it. That's what we have for you today. Thank you for listening. We're happy to reply to any questions you might have. Thank you.
Fantastic. Thank you so much. We have time for a few questions, if there is any. All right, yeah.
So you mentioned that you were downloading a shitload of APKs. What did you do for Play Store? Because it's not as trivial as I remember to download a shitload of APKs from App Store. So Play Store, Google Play Store, yeah.
Yeah, downloading directly from Play Store is a huge pain. Androzoo, though, gives you Play Store apps. They have a special relationship with the Play Store, and they are provided the apps directly from there, I believe. Androzoo is only available to universities. I think we had to ask for permission and get an API key from them, then we could download directly from them in bulk. So we didn't have to scrape the Play Store.
Okay, thank you.
Did you encounter any AI frameworks that actually also look at strings?
We actually didn't. We found a couple AI papers that said that it would be better if they looked at strings, but the issue was that they have an issue with the number of tokens. They say that if they look at strings and all constants, then the vocabulary would expand and be way too much for the model to consider. So no, we haven't actually run through. Maybe some exist, but we haven't seen them.
Thank you.
Could this also apply to iOS? Have you looked into this?
I am pretty sure it's the same thing. I don't know where native libraries in iOS are published to. I don't have experience in iOS, but I would expect 100% to have the same problem with outdating. The App Store definitely has a much more strict policy on keeping, the maintainers of the App Store will bug you much more than the Play Store to keep your app up to date, and all apps would get automatically removed. I knew some of this stuff, but I don't know the extent. I would not be surprised, though, to have similar numbers in iOS, but we didn't do this.
Mic number 4.
It seems like your simple bash script outperformed the state-of-the-art in some benchmarks. Did you consider trying to get this published as a paper?
No, look, the bash is very much a joke. I'm pretty sure that if you spend half an hour of it, you can double the performance of this, at least. And the thing is also, it's kind of a different problem, right? Those binary similarity machine learning frameworks, they also give you function similarity, right? Which is a different problem which we didn't even touch. So I'm not sure I want to say, oh yes, they all suck, use the bash. Maybe they just need to be complemented. Maybe you should use the bash to pre-filter them, and when you're left with 20 or 30 binaries, I'm pretty sure that playing and fixing the machine learning approaches would give you much higher accuracy than just looking at strings, because of course, strings would not have any code knowledge whatsoever, or maybe you can integrate strings into the machine learning models. I don't know, but I think we can just publish it as it is. It's nice for a CC talk, but depends on the reviewer, I guess.
Thank you.
Yeah, in practical applications of binary recognition, do you think there could be an example of adversarial examples, such as backdoor binary, which are specifically designed to fool both strings analysis and fancy analysis? And so how would you defend against that?
Honestly, I don't think there are many examples in the wild of people trying to do this, because it's so easy to fool any of those systems that even inadvertently you do it. There are some naturally very hard to detect binaries. For example, if you statically compiled a bunch of libraries together, it's going to get extremely hard to figure out the individual versions of those libraries, right? So you don't need to put a lot of effort. if people are doing it, I don't think so, because the systems we have nowadays will work so bad that it's not really necessary. But you could definitely do that. You can change the strings in your binary, have a packed binary, and all the strings are fake, and I don't think it will be hard.
Hello, thank you for the presentation. How did you determine if it is a real vulnerability or not in a library? Did you use some tools? Did you do some reachability and exploitability analysis?
So yeah, for example, in the app day, Samsung app, we reversed the app with JetX, and we looked at every instance in which the PL, Androzoo native library was called. We didn't use any reachability analysis tool, the automatic ones, because I had experience working with those, and I found them extremely unreliable. For big apps, for small apps, they work well, but if the app is more than 1 or 2 megabytes, it's much faster to do it by hand. So that's what we did. We didn't really look much into how much of those are actually exploitable. We plan to do this. There's going to be a paper eventually in which we have a very, very thorough examination of what is the impact of this. I would not be surprised to find quite a bunch of them, but yeah, that's what we did by hand until now.
Hi, thanks. Did you report any of these apps to their developers to maybe have them fixed at all? I mean, if they all stop at step 1, maybe someone should proceed at least to step 2.
Originally, in our project, we also got the email of the developer to alert them, kind of like the GitHub depend-about system, to let them one of the dependencies. This was our idea until we got the statistics and we realized that EPFL, our university, will not send us hundreds of thousands of emails because that's the amount of apps that were vulnerable to even a few basic CVEs like the ones I showed you. So we didn't do that yet. Honestly, I don't feel that much guilty about it because, for example, for the WhatsApp CVE, responsible disclosure was done 6 years ago, right? I am not super confident that now an email will get them to update. Maybe if we have an exploit, we can show a proof of concept that will push them to do that. But it's definitely a topic we will try to convince because we have those emails and we're going to send them. I don't have high hopes.
I mean, in the end, it's also on the best hopes of, for example, Samsung to have their app maybe fixed in the, at some point. But yeah, thanks.
I think we have a question from the Signal Angel.
Have you any plans on finding out what the remaining 8% of the unmatched binaries are, for example, by looking into obfuscated strings or something?
Wait, sorry, I missed the first part of the question.
Do you have any plans on trying to find out what the 8% of unmatched binaries are that you couldn't identify?
The percentage of obfuscated binaries?
Yes.
No, we don't have plans on that. Unfortunately, any automatic analysis framework kind of dies on the amount of binaries we have. So unless we find something extremely simple, like strings, it's not really going to work. Even one of the major problems of those machine learning models we showed is that the preprocessing was disassembling with IDA, which took how long, for example?
For example, 5 hours for the VLC libraries on JTrans.
Yeah, so just disassembly took 5 hours for 100 binaries, which is kind of a lot. So we're kind of limited on how much we can do. It would be interesting, but we don't have plans as of yet.
All right, Rocaille Hall, Luca Di Bartolomeo, thank you so much.
Thanks for you.